Today's presentation will be given by Gareth Williams from the National Composites Center. Gareth, please join me. Would you like to tell us a little bit about yourself?
Yeah, so I'm an aeronautical engineer by training degree. Did a PhD in self-healing composite materials, which you don't generally come across in your everyday life. I've moved from aerospace, well, I worked at Airbus for a while and then moved over to Australia. I've worked in marine, oil and gas, aerospace, so across a number of sectors, and looked at how we apply technology, materials technology, but a lot more future thinking. So what can it help us to achieve going forwards, and applied those principles across multiple sectors. So it's been interesting.
And what will today's presentation be about?
So I've called it the carbon revolution. So a bit of a provocative title, but we've got we're in a great position where we're looking at the future, and there's a big direction, a push towards net zero, increasing sustainability, and it's quite ironic how we have material systems that can be carbon-based, that can offer future potential to help push and drive towards a more sustainable future. So I'm going to explore some topics at quite a high level, but more than happy to go into a bit more detail as we go through.
Certainly, and certainly a very current topic. I'll introduce as well Luca Corradi, our Innovation Network Director. Luca, would you like to tell us why this topic is relevant for the oil and gas industry?
Sure, no, I'm very, very happy to have Gary here today. You know, the National Composite Center is an amazing facility and an amazing team of research and development, really at the forefront of new materials and composite materials. And as Gary said, and he will say more, these materials are really, really crucial, for the future of the industry, and both in aeronautic, automotive, but also for us in oil and gas. How can we design for disassembly and reassembly instead of decommissioning, for example? How can we leverage this material for the net zero ambition we have for the basin? So I'm sure that Gareth will cover all of that. And yeah, well, that's what I want to say.
Yeah. Well, I think actually,
the other thing I wanted to say, is we are starting a collaboration with the National Composite Center, and we are planning a couple of workshops in the new year, exactly for that reason. Right? So defining a strategy for composite in the oil and gas industry, and a strategy for that to be part of the net zero solution. So I'm really pleased that today is somehow the start of a journey in that direction.
Yeah, fantastic. Thanks, Luke.
Thank you, Luke, and thank you, Gareth. If you're ready to start, you're welcome. Your 20 minutes start right now.
Lovely. Thank you very much. Welcome, everybody. It's a real pleasure to be invited to talk today. So I'm from the National Composite Center, and we're part of the Catapult network in the UK. So our real purpose here is to springboard technology into industry and help industry de-risk some of the future thinking technologies to add benefit across multiple sectors. Sorry, you'll have to get used to me jumping around and figuring out the best place to stand in this one. So the carbon revolution. So in terms of a revolution, what we're really, if we go back to the terminology, a dramatic and wide-reaching change in conditions, attitudes, or an operation. So it's bringing about a radical change of any kind. So I don't think there's any denying that the pathway to net zero, the energy transition, is a very profound revolution, which will probably form multiple revolutions along the way. It's really interesting as I start exploring this topic. You look at the early age of humankind, it was defined by the development and utilization of materials. So you go from Stone Age, which basically gave us the tools to go and hunt more effectively, into Bronze and then Iron Age, which actually with it brought the creation of civilization, more communities, and more advanced technologies to actually further civilization. As we've moved into the future era, it's a lot more technology-driven, defined by the technologies. But there's two things that really underpin this that kind of get lost in the terminology that's used, and that's the change in energy systems that really have empowered us to go from independent material systems to a product architecture and deliver value through that mechanism. And the other thing is materials. So the materials are the enablement, they're the embodiment of the value that technology is delivering for us. So although the human modern progression is defined in terms of industrial revolutions and technology driven, as we move into Industry 4.0 in particular, it's really underpinned, and materials continue to expand the possibilities of human endeavors. So it's really interesting, carbon. So it's incredibly abundant. All life as we know it is carbon-based. About 20% of the weight of all living organisms is in carbon. So we all need it. When you combine it with oxygen atoms, again, we do need it, so it's an important greenhouse gas, but the problem is that we're pushing it to become a common polluter, and it's actually a bad connotation for that form of carbon. So it's currently about 412 parts per million, which is about a 10% increase on the levels since 2006. The irony for me is how, when you look at composites, and yes, there's a specific avenue of carbon composites, you keep the oxygen atoms away from these carbon atoms, you can generate some really powerful super materials that you can build on. So diamond, some people in the room will have some diamonds on their fingers. Carbon fiber, nanotubes, graphene are the more advanced applications of carbon. So, for example, to put it to context, carbon fiber is around 10 times the strength of steel. Nanotubes can achieve 100 times. Graphene, theoretically, can get up to 200 times the strength of steel. So that's how material can actually change how we view the product architecture going forwards. A little bit of homework here, hopefully. I'm not going to ask everyone to put up their hands, but if you can humour me on this one. So we've got 9 dots, you've got 4 lines, and you've got to collect all the dots without taking your finger off the page. So have a scribble, do it in your mind. I'll give you about 20 seconds to explore whether you think you can solve that one. And I'll move out the way so you can see it. I'm going to add this on the end of my 20 minutes. Right. So hopefully you've had a go at this one. I'll give you the answer. So 4 clean lines. What's happened here is the dots have a box around them. I didn't say that you had to stay in the box. Many of you may have just tried to solve the solution within the box. I've yet to meet anyone that's found out a way, other than using different dimensions that don't exist currently in our physical plane, on how you might solve that challenge. What does the box represent? So the box represents the boundaries, the envelopes that we put up around the product architecture, or barriers to innovation, just generally. So culture might influence that, education, experience, responsibilities, they define those boxes. Now, are those boundaries real? What I want to explore today is, can we actually push beyond those boundaries? Can we use material to actually leverage a way of going before that? How does it relate to something that's relevant technology-wise? If you imagine a performance cost curve, for example, in here's your product. So this is what you want to achieve. There's your box. So you're saying these are the variations in performance and cost that I can accept for that product. If you extend that a bit further, what you've got is a solution space for that product architecture. Some of that will be performance you don't require. Some of that will be at a cost that you can't accept. I think we've got a similar thing with the challenge for net zero. A lot of their solutions are in place, but there's no value in it. There's no supply chain development opportunity because we don't recognize the value of preventing carbon dioxide production. If we overlay that, so what we're talking about is a product architecture. If we overlay that with a material solution, you've got a material choice that will nicely hit the box that you've said I can accept. The challenge is if you don't consider the product architecture, you're potentially missing the opportunity space that exists outside that envelope. And the chances are that area, when you sum it up, is actually bigger than the envelope, the box that you've drawn around your product. More significantly, if you take a different material choice, it may intersect with your product, But if you're only talking about what the requirements are in this box, you potentially miss a huge opportunity of what that material can actually allow you to leverage in terms of your product architecture. Using a more relevant example, so thermoplastic composite pipes, they're probably one of the main wholesale changes that you'll see in oil and gas coming through, using composite materials. So this box is defined by, we want it lightweight, so it's going to reduce installation cost. And we want it no corrosion, because we're fed up of dealing with metallics that corrode in saltwater environments. What's the product architecture extension in this context? So the extension of usable product life. So using a different material that doesn't corrode, instead of 25 years, maybe you can use it for 50 years. If you can use it for 50 years, maybe you can redeploy it on multiple projects and change the entire value proposition of what that product is. Future-proofing, so beyond hydrocarbons. The chances are, if you make those products 50 years of operational life, 25 years might be in hydrocarbons. In the future, they might be hydrogen. They might be carbon dioxide. So why don't we think about how we use the material architecture to change the product architecture and future-proof these? And then into the more jazzy stuff, in terms of composite materials, you can embed sensors and generate live health monitoring, so you can actually understand the performance of the product. Current constraints in that product architecture, so why it's difficult to achieve these: manufacturing, transportation, installation. You've got the product architecture to support this product, and that can be limiting in terms of realizing the full potential in this application. You're dealing with existing infrastructure and existing capabilities. If you only have one vessel, and you're just going to redeploy that using a lighter weight product, you're not saving on installation costs. So it's just getting that cascade effect of different technologies. Future product architecture. So we're looking more into the digital physical hybrid. So what does that mean? So we start from a basis that says, I'm going to look at the operational envelope, I'm going to understand the functional requirements in terms of what I need something to do, and I'm not going to constrain it straight away. Digitally enabled design, it's characterized, it's rapid, it's complex, it's validated. You have a separation into that hybrid environment now. So you go through physical validation tests to determine whether it's fit for purpose, whether it meets the requirements, it's representative, it's confirmatory, and into the virtual qualification environment, which means you're much more rapid in terms of your time to market for new product. Coming back into that convergence, you've got to manufacture something to be able to use it. So how we use the digital physical systems to actually sensorize, control, and really importantly, record. So a digital thumbprint of the product that you're creating, which leads to then another separation. So you've got the operational, it's sensorized, it's monitored, it's live. So you use this digital thumbprint to create a true digital twin. You use your sensorization to actually keep and monitor that technology in operation. It helps bring down some of those barriers to entry. And more importantly, with composites, in terms of the future space we're trying to push them, is about end of life. So how do you design up here for reuse, recyclability, redeployment, and more into the circular economy, which I'll touch on a bit later. Composites is a mature market in aerospace. In 1903 was first flight. It's really interesting. It started with wood and fabric, which are a form of natural composite. Where's it going? 2015, the A350XWB, more than 50% composite material. So using that material actually extends the capability of this product architecture in terms of range, fuel efficiency, reducing fatigue issues. Oops. What's the vision of the future? So in 2050, the vision of the future is actually going full circle back to how we get more inspiration from organic materials and apply those benefits. So we're talking about biomimetics, so using biological inspiration to generate tunable materials, designed materials, live materials that can respond to stimulus. So this is the vision from Airbus in terms of what their future aircraft will look like. So you can make translucent panels depending on the stimulus. What you'll see from this, though, is that the material has not necessarily influenced the product architecture. Still got two wings, still got a tailplane, still got a fuselage. It hasn't changed drastically. But what we're seeing now is more of a diversion. So future air mobility is into autonomous vehicles, it's hybrid between land transportation, urban mobility, and into future frontiers in terms of spacecraft. The spacecraft that Virgin Galactic are launching, the Stratosphere, I forget the name of the aircraft. The launch vehicle is one of the biggest all-composite aircrafts in the world, launching vehicles up into space, which opens up all kinds of avenues in terms of space tourism and exploration. So the advent of new materials is really enabling the future of flight product architecture. It's enabling us to change that. What does it mean for renewable energy? So currently, offshore wind is an incredible story of scale. So 2000, these are about 2 megawatts, 90 meters. The rapid expansion of that scale has come up to, this is an A380 aircraft, which people consider pretty big. These offshore wind devices, the biggest all-composite blade currently manufactured by GLM is 107 meters long, which is astounding in terms of scale. So we're working on what will be the next scale. Is it a continuation of that product architecture and get up to bigger scale? Or do we change the product architecture to make it a more efficient system? Increasingly, it's going into floating systems as well as we look to explore different areas of the seabed for renewable energy. So you can imagine if you're putting something of this scale, which is effectively then rotating 3 Eiffel Towers around a floating mass at the top of a tower, it's a pretty significant engineering challenge. So we're trying to push that a lot more into the digital environment to make sure that we've got a really rapid development of that new product architecture. We also need to be comfortable with diverse energy systems. There is no one-size-fits-all. There's a plethora of energy systems. So scale will push the new limits of the product architecture. We'll see diverse renewable systems, multi-energy solutions, and it'll be the right energy for the right application. Future energy. So the material possibilities are there to expand the future energy product architecture. What are we talking? So we're talking more integrated, so offshore energy hubs where it might be oil and gas with renewable energies combined with hydrogen and carbon sequestering and utilization. It'll be balanced, so it'll be offshore wind, wave, tidal, solar in a combined system. It'll be common, so it makes sense to use common offshore infrastructure to reduce the cost barrier to entry for some of these technologies and to share efforts. It'll be mobilized, so if you imagine a future where these composite pipelines and TCPs are 3D printed on the back of a vessel, you're eliminating a huge amount of those constraints in the system. On location, and then you have subsea processing and storage that these materials can enable because they're not actually responding to the environment by corroding. So modular as well, modularity and standardization is going to come and be more significant as we change to these materials or they influence the infrastructure. So if you imagine a Meccano set of lightweight modular structures that can be reconfigured and redeployed, they may be used for offshore oil and gas, hydrogen, carbon sequestering, or even renewable energy. So you've got a potential common platform. They'll also be digitally connected. So the energy transmission through energy transmission, whether that's a direct wire or some form of transportation of hydrogen, but also data connection so that we can have live, up-to-date information on how that infrastructure is actually performing. And remote. So increasingly we'll probably want to remove personnel from the systems offshore so there'll be more autonomous ROV systems that can monitor, maintain, and we rely on the wireless information we receive of that infrastructure. And more into sustainability. So we're using the term and we're developing an initiative around composite sustainability cubed. Why cubed, I hear everyone ask. So there's 3 pillars to the fundamentals of sustainability and composites. We've talked a lot about the product architecture and how we're actually optimizing these structures for lightweight, reduced corrosion. That's how you get the value out of these products in operation. But where the other strands come in is where you have the start of life. So you're talking about new design. How do you design for disassembly? How do you design for end of life, modularity, reuse? What is the future application going to be for? And end of life. So when it gets to the end of its current life, do you decide to repair it? Do you decide to reuse it and redeploy it? Or do you decide to actually recycle it? And there's an opportunity then to go back to raw. So you return those materials into the next product architecture in the same industry or maybe in a different industry. So what we have is a cascade effect. So from high performance, low volume applications where the material performance demands are really high to more of a low performance, high volume infrastructure application. So the analogy would be if we take high performance composite wings, we recycle them back to raw, we step them and then make wind turbine blades out of the same material. At that end of life, we recycle them, we put them into offshore infrastructure, we put them into vehicles, and then at the high volume end of that, we put them into infrastructure. So we're talking road bridges, we're talking walkways, and ultimately you can use it to reinforce concrete structures. So it's really paves the way to a more circular economy where those materials enter the system and have a direct application, the systems, the knowledge around it to see where that material can be reapplied and add value in another sector. And to get that circular economy, it's that recognition of that value that's required. Because at the moment, there is no incentive currently for these guys to produce a recycled material to go to these guys. So that's the position that we're working on. We're very well connected across all these sectors because we're technology focused. So in the future, I would hope you to expect to see some stories that will be working successfully in this space and hopefully demonstrate that we'll have future energy infrastructure made from recycled materials from other sectors. And I think that's about it.
Thank you very much, Gareth. That was an interesting presentation. Surely interesting to consider how materials influence our products, applications, and how it all fits into the circular economy. We're now opening the floor to questions. We'll have 20 minutes, and we ask you to wait for the microphones to come to you because we're recording, and so that everyone can listen to what you're asking. Do we have questions? One over there.
Hello, thanks for such a lovely presentation. It's really, really good. Is there any room for recycling all the plastics that are in the Pacific Ocean? You know, just that mess can be utilized some way.
Yeah. So again, it's understanding the material requirements and the product architecture you're trying to enter. So, I mean, we've got examples where, so one of the ways you can add stiffness into a structure with composites, you have two skins and you have a core. So that core can be some form of foam, it can be balsa wood. We've done a project with Shell where we've actually introduced PET, recycled PET foam core, and introduced that into their structures as a composite. So the use of marine plastics, yeah, absolutely. It comes back to that characterization of when you recycle the material, what is it? How long does it last? What is its structural performance? And those are critical pieces in this pyramid to actually identify and characterize the different waste streams and where they can re-enter the market. So absolutely.
Would that be that you can put all the plastics together and create a material as a fusion of all of that? Or because I guess you need to track what you're doing. You're saying going from one very demanding situation to one that is no demanding at all. But obviously, I guess that you need to track the life of the material, A, and B, you need to probably, I guess, separate those composites or those plastics in order to get the purest material that you can get.
Yeah. So I guess the thing that supports a lot of the value stream in recycling is the high the high cost, high performance items. So primarily what we're talking about in the recycling from a composites perspective. So a composite, you've got the fiber and you've got the resin as a matrix. So that's the plastic aspect. But the fiber can be carbon fiber, glass fiber, aramid fiber. It can be natural fiber derived from hemp or natural sources like that. So generally what we're talking about in the kind of near to market value stream is about recovering the fiber, because that's the high performance. You've got high performance, high cost carbon fiber that are going into aircraft. And the key really in that is to remove the matrix so that you can repurpose it. It's different if you talk thermoplastics, where you could use heat to reform those structures instead. So it might be a different proposition in that context. It's slightly separate to what the plastics recycling environment would look like. So we're talking PET bottles and things like that. So there's I guess two streams. So in composites, we're talking more of the high performance structure where you've got really high value product fibers that you really don't want to just be putting into landfill. And in the future, you may be combining them with polymers that are sourced from recycled material or through repurposed carbon sequestering to generate new chemicals that may then enter the market as well. But if you look at third world developing countries, there's the opportunity to put recycled plastic material into building materials, and you may reinforce that with low-cost carbon or low-cost glass that has been recycled, from down kind of this level when it's re-entered the market.
Are there other questions? Yes.
Do you see this as an economic proposition initially, or do you think this needs to be driven from a regulatory point of view? So telling people that they must create materials that can be reused initially, mandating it through regulation, and then later on as it kind of develops, it then becomes an economic proposition? Because the lifespan that, I mean, I don't know about aeroplanes, I've no experience in aviation, but in oil and gas, we talk about 25-year design life is reasonably standard. The value in something that something has in 25 years' time is relatively small due to just the time value of money. So to make this an economic proposition, you're always fighting against the fact that it's going to be quite a small economic driver if you are realizing the value in 25 years. Does that... Yeah, I got a bit rambly, sorry. Did that make sense?
No, I think I've picked a couple of streams there. I guess the first thing when you talk economic value, if I go back to the product architecture, the current economic value may be limited, but if you change the material and you take your 25-year design life, but you've actually got another 25 years of usable life, it becomes a high value proposition to then re-enter, either extend that product or then recycle it and put it into something that has a long-term benefit in that sector. The other side of it is the regulatory side of things. Absolutely, you can't do these things without, I guess I always say, the carrot and the stick. So you need someone that's banging people with a stick that's saying, thou shalt recycle. You have to provide that because it does drive the right behaviours. But you also need the carrot, which is the economic value proposition of re-entering the market to someone that's willing to pay for it, because it's probably a lower cost alternative than raw materials for them. If that makes sense.
Yeah.
Hi, a really interesting talk. Noticing your pyramid and seeing a similar talk on battery recycling, like especially car battery recycling, there seems to be a big issue with the secondary and the tertiary industries because they're not getting the feed in of the raw materials for them, or they use materials from us, aren't feeding into the secondary systems as it stands. So they're not. So the primary users are just going, well, what we're doing with this at the end.
Yeah.
Because they can't predict, as the gentleman was saying, 25 years down the line, who's taking this stuff off me, sort of thing. That you know, they can, unless a single industry can reuse it into itself, how does a new industry sort of hold? Yeah. Withstand sort of 25 years to go, I'll take it as soon as it comes out, 25 years?
Well, I think that's the role that part of the reason why government-initiated organisations like ourselves and the OGTC, and why we're working together to help bring some of these sectors. So there's a collision of sectors that says we've got a product that's got some value here, we've got a product that needs a supply chain or a material or whatever that is, and we demonstrate through case studies, through technology development, bringing people together, how that can actually work. You're absolutely right. If it's left in isolation, then you're coming back to the previous point. You're relying on these commercial drivers or political drivers to make something happen. So I see definitely the role of catapult centres and organisations like the OGTC working together to help industry de-risk some of this and paint a better picture about how this might work. Absolutely.
I guess just before question, it's pretty much impossible to get carbon composite recycled at the moment, apart from dumping it in a landfill. Is that a fair statement?
No.
Anyway, just a general question, more general question. I would say the speed of uptake in the oil and gas industry of composites has been relatively slow. Why do you think that is?
So I'll address your first point. So recycled carbon is a thing. We've got a number of companies that are involved in that. And to put it into context, we held a workshop on a cross-catapult initiative called Rediscover, which is around composites recycling. We had somewhere between 80 and 100 companies attend that workshop that are interested in developing this supply chain. We've delivered products based on recycled materials, recycled carbon fibre. The key thing right now is also supporting that with the customer demand. So you need an application to put that, to drive the economic model that means that companies are going to invest in those technologies. So it's fairly new and emergent technology, but it's a real thing, and I can bring it. Maybe I should have thought about bringing in some samples, but yeah, we've manufactured components with recycled carbon fibre. You also have waste carbon fibre that comes out of a manufacturing process. There's tons of waste because they're generally not manufactured in wing-shaped parts, which is raw material that can re-enter the recycler market as well. Remind me of the second piece. Oh, yeah. I think there's a couple of drivers for that. I guess the first thing is when you look at the product architecture box that I drew, you've got a defined product architecture you're working with. Those materials don't necessarily extend that significantly. I think the drive towards net zero is driving that agenda a lot harder because the efficiency gains in the industry have been driven through known materials, doing things better, more efficiently. The opportunity now exists to look at different product architectures, different materials. We can make pipelines, we can make Christmas trees, we can make manifolds in composite materials with technologies that exist now. But we're using that material for the existing product architecture. There's another layer of opportunity that exists that say, okay, if you're building it out of this material, how should it best look? How should it best, exist as a product architecture? And I think the reluctance is you've done amazing things as an industry based on the technology you know. So what's the driver for change right now? And hopefully I've touched on a few drivers in here. So I've been working as in this sector from a composites perspective for about 4 years at the NCC now. And the change in level of conversation with oil and gas companies has gone up exponentially. So we've got live projects that are demonstrating the use and the benefits of composites in real oil and gas applications right now. So hopefully you'll get to see some of those in the various channels soon.
I was wondering how the classification bodies accept the new materials to replace sort of traditional materials, because they can sometimes be a hurdle.
Absolutely, yeah. So TCPs is a good example. I think the only thing in the market really that exists that give you any kind of guidance towards how you might meet that is the DNV recommended practice, which is why the work that Luca's referenced going forwards, we have to bring the certification bodies on board so that they're inherently part of the process of defining what the future product architecture is and not closing down the opportunity for new materials to enter that market. And that's what we're working collaboratively to help support industry to achieve.
Can I ask about a major incident with carbon fibre? An example would be a Formula One car crashing and you see carbon fibre goes everywhere. Is there a way of protecting it for more general wear and tear. I'm not particularly asking about, sort of major instance, but you see it split all over. But is there a way of protecting it?
So one thing I'll come back on that first point. So the reason you see it flying everywhere is by design. So in a Formula One crash, you want to protect the central body and the person that's driving the car. So you won't see much flying off that part. The rest of it is designed to actually release energy from the system and take that away from what you're trying to protect. So it's actually by design rather than by properties of the material for that. Although composites, do help in that. It's all around design. So the difference with composite materials is, and where you have to really understand what you're trying to design in quite a lot of detail, is they're layered. So each ply of composite material generally has properties in a specific direction aligned with the fiber. So you can get woven mats that change that. And then you layer them up. So what you generally have is less performance through thickness, where what you're used to dealing with in a metallics and a pure polymer context is a homogeneous material with equal properties in all directions. So that can be a downfall if you literally take a product that's designed for metal and try and introduce composites in that application. You'll get a benefit, but it won't be optimized for the material that you're using. So if you take the design envelope and design around the material, you can actually design out most of the challenges in terms of robust material. So it's a fair challenge. A lot of the mature markets like aerospace, like Formula One, they're driven down that avenue of composites primarily for lightweighted. It's a big value proposition for that material. That's why it's developed. And I hope you're reassured by this. These things aren't lightweight structures. So when you're flying on them, there's all kind of design loads. And I hope none of you will encounter anywhere near what these materials are capable of achieving in these structures. It is, a fair point within the heavy industries. You've got to think a lot more carefully about how you use the materials and how you might install it. It's not necessarily a cut and paste, right? Just go and install this product in the same way you always have. You can't bang them into shape with a big spanner or a hammer in the same way. So it's a cultural change that needs to be done in terms of skills and education to support that as well. But it can be done. But it doesn't have to also be wholesale change into just composites. So metallics will also always play a part. So you can have hybrid structures as well, particularly in high wear environments. It may be better to put some form of metallic surface in the structure, and you can integrate that in a composite structure as well.
Hi, I'm Richard. I remember reading in the back of the Sunday Times they had stuff about carbon nanotubes, graphene, that kind of stuff, and you could build the Brooklyn Bridge with a string of carbon nanotubes or whatever. And now you don't really hear very much about it. And I know there's a centre somewhere in England developing it. And I was just wondering what you know about it, where it's going, if there is actually such a thing.
I mean, the new, I guess, I forget the terminology. I actually anticipated a question like that coming up, and then I didn't do enough homework to prepare my answer. But yeah, I mean, when you look at the advent of new materials, so where people drive materials development, you get a spike in interest. So everyone's talking carbon nanotubes, and at one point everyone was talking about graphene. And then people kind of peter off as you try to find an application for that, which is exactly what you've just described there. So you hear a lot of talk about super materials, new materials, and then people struggle to find an application. That's when it's driven from a material development perspective without necessarily an end application in place. But if those two things are combined, so you're developing the material requirements with the product architecture and they're actually a cohesive unit, then you get a better situation and a solution out of that. So we are using carbon nanotubes to strengthen composite materials. It's a lot further ahead before you'll get carbon nanotubes of the length that might span the Brooklyn Bridge. But there are applications for graphene in composites as well. But you always get a bit of a chicken and an egg. So you develop these new materials, they're very high cost, so everyone goes, well, I can't use it because the cost isn't there for me. But you need an application to be able to industrialize the process. Again, those are some of the roles that Catapult Centres help to support, and I think there's a Graphene Institute that you've referenced has been set up specifically to try and help to introduce graphene in different markets. But because of its nanoscale, it's not just going to influence the product architecture like this, it's going to influence probably microelectronics and all kinds of different interesting markets.
Sorry, just a really quick question. Microplastics, obviously.
Sorry, I didn't.
Microplastics.
Yes.
Obviously, you're talking about nano sizes, and you pointed out earlier there's the wastage from the carbon fibre industry. Is this a concern, and how's this being combated?
So microplastics generally occur, I'm no expert, but occur when you have liberated plastic waste and it starts to break down and you end up with microplastics. We're not talking about the same situation here, particularly when you put carbon nanotubes and graphene. They're locked into a resin matrix and that's part of the reason why recycling doesn't happen readily. They're quite difficult to get back out again, so you don't suddenly have a cloud of nanotubes creating a biohazard. Microplastics is not really a thing because you're generally designing these structures to not degrade, and inherently the materials you're using are not designed to degrade. Or if you do want them to degrade, you want a specific stimulus that you can introduce. At the moment, that might be chemical, it might be heat, but in the future, as we get to more really thinking about how you design for disassembly and how you generate the chemistry required to achieve your end-of-life solution you want to achieve, then you're talking about different ways of actually deconstructing that structure. But the point is it's controlled. Because the last thing you want is to be flying on an aircraft and the material decides to degrade itself. Hopefully.
Thank you. I was just going to ask a very quick question. My name is Pamela Lamora from the Oil and Gas Technology Centre, and I'm a materials engineer, so I quite enjoyed your presentation. You didn't touch very much on manufacturability. Can you just elaborate on that? Because I think that's one of the challenges in bringing this technology to today. And in terms of recyclability, you've talked quite a lot, but I think that's for new products. So designing for new products and not necessarily for enhancing or repairing existing infrastructure.
So designing for manufacture actually is a massive thing for composites, because you have to be very much thinking about how you're going to manufacture it when you select the material to manufacture your product. But we've got projects in train right now where we're working on TCPs, flexible pipelines, subsea structures, and that's not necessarily in the first instance changing the product architecture. So it's absolutely possible to make something like the support structures, the main structural components of that with existing composite materials. I could do that tomorrow. So manufacturability is not an issue. Then it's just whether the price point, the installability, all those other lovely, through that Totex lens, come into it. I forget your last point, sorry.
Are you able to redesign for, design for repair of,
yes,
say, repairing an infrastructure that is not composite and has other parts that are not composite?
Yeah, ironically, one of the most immediate and probably widely used uses of composites in oil and gas is to repair corroded metallic structures. So pipelines that are corroded generally will use some form of composite wrap, because it's really conformable. You can put it over the top of the metallic layer, and you can provide a watertight structural seal. I've done it on boats as well. Composite aircrafts have their own design repair schedules using composite materials. So repair is absolutely a thing. The ideal is you design the structure not to need repair, and hopefully you've got sensors that will tell you in advance of when you might incur a load that would require a repair. So I would rather avoid the intervention requirement for a repair, but it exists. So composite repair is a big area.
We have unfortunately run out of time for more questions. Thank you, everyone. It has been a lively discussion. If you would like to continue the discussion, we do encourage you to move upstairs to the TechX Lounge and continue any discussions. Thank you very much, Gareth, for the presentation. It's been really interesting.